Hi, everyone. So I'm Edward. I'm a last year PhD student at KU Leuven University in Belgium. And this is a joint work, so indeed like with multiple people, but also, but especially with Bastian Rieck, which is here. And this work was done while I was doing like a research stay at ETH Zurich, so in the MLCB group, where Bastian was previously. And yeah, maybe Bastian, you want to say a word about yourself as well?
Yeah, sure. Hi, I'm Bastian. I'm currently a PI at Helmholtz and TU Munich. And yeah, it's a pleasure to be here and listen to Edward talk about this work. So thank you also for the invitation and this opportunity.
Awesome. So yeah, so here you can have like you can put a face on the names which are on this paper. So it's also with Max also as a joint first author, but he could not join today. So this work was published at ICLR this year, and we had like good feedback. So I'm just gonna try to give like a bit like a longer presentation about what we've been doing in this work. So maybe to just like put us up to speed, like just like a very quick recap about like graph neural networks. I know that like the whole audience here is like really familiar with this type of topics, but I think like it will help us just to put us on the same base.
I disagree and would skip it.
Sorry?
I disagree and would skip it.
You would skip it? That's what you said?
Yeah, I would.
Oh, okay. I mean, I can just do in 5 minutes, I guess, like, but it's just like, so basically what we're trying to do is like, yeah, so learning like representation of a graph. So like having like some, to be able like to do some classifications, some regressions. So as you all know, like graph neural network or like graph convolutional layer would operate like locally on the graph, which is actually like a very important difference with our approach that we're gonna like come up like in the next slides. So where you're gonna have like basically kind of like the three basic procedures. When you want to aggregate like information from neighboring nodes, you're gonna combine them together. Then you're gonna iterate that like for a certain like number of times, of number of layers, and then you're gonna have a readout at the end of the process. So very quickly, so yeah, so you have like graph like this, and indeed like for each update like a graph v4, then you would just like aggregate like the node features which are local to this v4, you would combine them and then like update the representation. So there's like a lot of works on this, of course, you all know, and probably like you've been working in developing like extra methods for this type of task. But yet like despite like the popularity of this approach, it has been shown also that like there are like some limitations in the expressivity of this type of like of graph neural networks, and especially in graph convolutional networks. And for instance, a very striking example is the one that we're showing on the slide, which I think is very popular as well, is that like is well known, and like a GCN cannot really distinguish between those two different graph examples here on the slide. So basically like between a graph which would have like just two different connected components with just like two small cycles, and then another graph on the right with a larger cycle. So yet if you think about this from like a topological perspective, it should be obvious to be able to distinguish between those two graphs. So first of all, because they have like the one on the left has two connected components, the other one has just one. And also like the one on the left has two cycles, while the one on the right has like only one cycle. So the questions that we were asking here in like this whole work, in which was like pervaded like a whole investigation, was how can we actually imbue graph neural networks with like topological awareness, topological information, such that like this type of like easily distinguishable graphs from a topological perspective could also be distinguished by general graph neural network architectures. So to do that, we're gonna use a filtration. So what is a filtration? So we're gonna define like a function f, which operates on the node features of each of the graphs. And that will return a scalar. So it's a scalar function. And we can consider, do you see my pointer actually? I guess you see it, or yeah. So we're going to consider that we have like node features at each node, which has dimension d here. And here fi to f1 would be basically like kind of like different thresholdings at the value of this function. So we're going to define a filtration on like a general graph G as a nested sequence of subgraphs that follow this property. So basically what what the equation says here is that like you're gonna apply your function to each of the different features, like node features, the nodes on your graphs. So here I have like two examples. Like for one the filtrations on the top would like give like value 1, 1, 3, 3, 2 to all of these nodes. And then let's say another filtration that would be like another filtration function. So another function here, f, would give maybe like 1, 2, 3, 4, 5 on those different nodes. So with the same node features, but basically because it gives them a different function. And then the way that we're going to compute a filtration is that like we're going to basically sweep on the values of f, and we're just going to keep the nodes and the edges in the graphs that follow this property. So basically that like such that the value of the function on the nodes is smaller than the threshold. So this f of I you have to think about is like kind of like a sweeping function. And we're going to keep the edges such that like basically the nodes that those edges connect are still in the subset at that value of the sweep. So basically that gives this value. So if we just we sweep until like when actually there is a change in the filtration. So when it's lower than 1, basically you don't select any nodes, so you don't have anything. And so your first value of interest, which would be like f of 1, would be 1 here in this case, where for filtration 1, we would have like those 2 nodes on the top that would be selected, and on the bottom, like only 1 node. Then the second graph, so which would contain, of course, like the previous one, because it's nested construction, would only contain like those 2 ones. So the nodes which are like smaller or equal to 2. And then the third one would contain the nodes which are like smaller or equal to 3, and then the fourth one like this, and then the fifth. So I hope that it makes sense. And so at the end of the day, what you have is that like you have a sequence, a nested sequence of graphs that have been generated by your filtration F. So once you have this, what do you actually do with this? So you have like this filtration. So you have like the sequence of graphs that evolve with the value of a certain threshold based on a certain filtration function F. What you can start doing is that like looking at the persistence of topological features. So what you're gonna do?
Can we ask questions?
Yes, sure, of course, please.
Sorry, I just want to understand everything.
Yeah.
I am sorry for this stupid question. So can you look at this filtration as counting the subgraphs of the whole graph, or I understood it wrong?
So not necessarily. So what's going to be important here is that like depending on the filtration function that you're going to choose, you're going to end up with different sequence of subgraphs in your graph. So it's not like you're counting all of the different possible subgraphs in your graph. It's just that like based on like this filtration function here, you're going to basically like assign an order. That's what it's going to do, like an ordering of the nodes that you're gonna like include in the graph progressively. Does that answer your question?
Yeah.
So if you consider, for example, for this particular graph that you have here, like this 1, 3, 1, 3, 2, if you consider the after the first filtration, how many elements does this set of the nodes have and the set of edges have after one filtration, one particular filtration that you have in mind?
Can I maybe? So the filtration are just different orderings that we're defining, right? So we're like every filtration is one of these functions that gives us numbers for each node, and according to those numbers for each node, we sort our nodes and then create subgraphs based on that sorting of the nodes.
So it's like it's a permutation of the ordering of the indices for the nodes. something like that.
Yeah, somehow you could see it like that, right? Because like one of the so here you see that like you can have like the same filtration value, like the same image of like filtration function for two different nodes in the graph. Here you have like one on one, but like that's just a technicality. But for instance, for the gradient to be well defined, you're gonna need always to have like a slight differences in the image of the filtration function on your on the different nodes of your graphs. So down the line, what it comes up to is that like you're gonna have, as you said, like it's a different ordering of all the nodes in your graph, and then based on this ordering, you're gonna construct like the sequence of subgraphs which contain all the nodes of that graph in that order, if that makes sense. So that's why here, for instance, let's take the one on the bottom. That would give like 1, 2, 3, 4, 5. That would actually assign an order in which you're gonna actually include the node one by one. And that's why at the beginning, you only add those node 1, then the subgraph number 2 would be like only those 2 nodes. Then number 3 would be this one. You will add this edge because like there is an edge between those 2 nodes which are actually included for like this and 5 like this.
I see. Okay, that makes sense.
Awesome. Yeah, no, I think it's kind of, I think when you get it, it's kind of intuitive, but indeed like just writing in a way that like this that actually renders this clarity that when you have when you have actually understood it, it's not that easy, if that makes sense. So yeah, so now we have this filtration, which is like the sequence of subgraphs of the initial graph G. And what we're gonna do with this is we're gonna study how different topological features of the graph, of basically of the subgraphs, are going to persist over time as we increase this threshold, right? So what we're going to define here, so like for instance, what are examples of topological features? Very easy ones are, for instance, Betty numbers that would like intuitively count the number of certain prominent topological features in a graph. For instance, like the Betty number of dimension 0 would be basically the number of connected components that you have in your graph. Number 1 would be the number of cycles, and then you can go on and go forth, but it's, yeah, of course, it increases in complexity.
What's the Betty number? Number 2.
So it's the number of I think it's the number when you have actually like, so when it's a simplicial complex with 3 with, I guess. No, Bastian, can you maybe?
Yeah, it's the number of 2 clicks then. So
yeah,
so 0 clicks, 1 clicks, and 2 clicks if you go higher.
What are 2 clicks?
2 clicks are fully connected subgraphs with so basically triangles, fully connected subgraphs with where you have pairwise connectivity between all of them.
Okay, and what is a click then? I thought, so what's the difference between a click and a 2 click?
You can have them in higher orders. I mean, maybe I could also give this over to Edward. Sorry, I don't want to hog your time, Edward.
No.
So it's a fully connected subgraph of k plus 1 vertices. Yeah, right. K plus 1. There's always a shift. So 2 click is a fully connected subgraph with 3 vertices, which means a triangle, and the 3 click is the same with 4 and so on. Those are kind of a scaffold of a data set or of a graph.
Just a number of nodes. Okay, but then Betty numbers. So the k equals 2 is the number of triangles, and the k number 4 is the number of cliques with 4. The k equals 3 is the number of cliques with 4 nodes.
Yeah, I was a teacher or something. They're fully connected.
All right, thanks.
So then you can compute basically this number for the different dimensions for each subgraph. And this and what you can do is then like study how actually this number of specific topological features like persist in your filtration, so in the different subgraphs. So basically like beta I, j, k here would be like the case Betty number, and so how many of like those features basically persist from I to J. So basically from graph I to graph J in your filtration. And so this will give you like an idea, like if it's more persistent, basically of the importance of these topological features also in your graph. And you can then build a persistence diagram by storing each point and basically Fi, Fj, which like corresponds like to different thresholds basically of your filtration functions in the graph with some multiplicity, which will be given by this function. What this accounts to doing, so just to give a better impression, is that like if you have like a graph filtration like this, you're gonna count like, for instance, at a graph 1, what is the Betty? So here we're gonna call like check the Betty number 0, so the number of connected components. So at graph 1, you have like basically like two connected. You have two connected components. So basically you have like Betty number 0, and this feature is gonna like continue up until at least the filtration value, filtration function value 2. At which you're gonna actually add another connected component. So actually you're gonna have like a Betty number that goes to 3 in G2. And then at G3, basically you're gonna connect all of those 3 parts together, meaning that you're gonna get actually like end, you're gonna kill basically like 2 of those connected components that will stop at time 3. And then another one, because you still have one graph, so you still have at least one connected component that will continue until basically infinity. And this representation, which is called like a barcode persistence diagram, encodes really so the persistence of like those topological features in your filtration. And based on this, basically you can then, so that's a way of encoding like the topological features in your graph. So you can do this like for beta 0, but you can also do this for beta 1, where you will see that basically you're gonna have like the birth of such of a cycle at F3. And this is going to continue for infinity because you're never going to destroy this cycle. And so basically based on like the filtration function that you have, it is going to give you a filtration of graphs, and this filtration of graphs then will give you a barcode persistence diagrams that depends both on this filtration and on the initial topology of the graph. Because it's going to encode like how different topological features are persistent over time. So from previous work, we know that we can already learn a filtration. So basically we can learn this function f here, such that actually it represents, it gives us like a persistence diagram here, which is the most informative as possible for a downstream task. So that's been published at ICML 2 years ago. But this was only used for basically a readout function. So now what we're asking is that like, can we actually create a layer that actually would basically learn a filtration function to compute this persistence diagram and then be stacked at like any position in a graph neural network architecture in order like to imbue topological information in the flow of information in this graph. And that's what we do in our layer, which is called TOGL. So it's like a topological graph neural network layer. And so this is basically like the overall schematic of what this layer is doing. So you first start with a graph here, which will have like different node attributes or node features. And then we're going to learn k different filtration functions that will then give us like k different filtration values on each of the nodes of this graphs. So we have kind of like a bank of filtration functions, and we have k of them. Then, as we saw, as soon as we have different filtration values for each of the nodes of the graph, it implies a filtration of each of those graphs, and we can compute like a persistence diagram with this. So the persistence diagram can also be seen as like a set, basically a set of points. So basically a set of points, like here you would have like 1 infinity, here you have like 1, 3, 2, 3. So you can basically see this as a point cloud in some sense. So we use some aggregation function that we're going to take this point cloud for the persistence diagram and concatenate it with the initial node features of the graph. So basically we have like a node embedding for each of the graph.
Excuse me?
Yes.
Yeah, just to be clear, so there are K persistent diagrams?
Yes.
Yeah, thank you.
Welcome. So we have like the scale persistence diagram, and then we aggregate like in a residual fashion with the initial node attributes, and then that we can map back to the same dimensions of the initial node attributes. And this way we can then attribute, or we can assign a new feature vector for each of the node in the graph that contains topological information. And because we go from a graph at the beginning to a graph at the end of this stack, we can basically plug this in any location or at any level in a graph neural network architecture, because we have from a graph to a graph. The only difference now is that, like in classical graph neural network architecture, you would basically update your node features with like just local information from basically your neighbor, the neighborhood of each node. While here, your node attributes will now contain like global information about the graph due to the processing of this persistence diagram. So what's nice about this is that like we have like interesting theoretical guarantees. So we know that like typical GNN architectures are no more expressive than WL. But we can show that actually persistence homology is at least as expressive as WL, which means that we can show that we can always, there always exists like an injective filtration F, such that the persistence diagram will not be equal if the WL of two graphs diverge. So basically, if you know that you have two graphs G and G prime that do not have the same WL representation, you know that there exists a filtration F, and so a filtration function F. And basically, if you parameterize this filtration function by a neural network that has like universal approximation property, you can definitely show that you can probably learn such a function, and there exists then such a function such that the persistence diagrams won't be equal. And so based on the fact that they are not, those persistence diagrams are not equal, you're going to be able to distinguish also those two graphs. So just to come back like to the initial example that we had here, so we see that like G and G prime, like very classical GCN, cannot be distinguished. But here, if we just count the Betti numbers, so beta 0 for G is equal to 2, while the beta 0 for 1 is equal to 1. So that's a feature that we incorporate in TOGL. So basically, directly, you can distinguish that they are not the same. And same for beta 1, which would be like the number of cycles. Here you have 2, and in the one on the right, you have 1. So basically, you can distinguish them perfectly. So we ran like a bunch of experiments in order like to assess what about the performance of this model and how like different setups were actually performing. So our base experiment that we do here is we take like a classical GCN architecture, so like a GNN neural network with 4 convolutional layers, so 4 stacks of GCN. And what we do is like from the stack, we just replaced one of the GCN layer by our layer, TOGL layer. So basically like to be like very fair in terms of comparison, because it's not like adding more computational power like on top of it. It's just like swapping one of the GCN layers by a TOGL layer. And then we're going to assess the expressivity on like synthetic data sets just to validate that our approach is actually like doing what it's supposed to do. And then predictive performance on data set without node features, and then on benchmark data sets.
But don't we still have more weights in a TOGL layer than in just a GCN layer? Because we have the weights computing our filtration and so on.
Yeah, so indeed, so we show that like basically that like so I don't remember the numbers by heart, but like we show that like the number of parameters is like roughly equal. Because like we share still a lot of weights among all of this like in the layer.
Okay, so
because like for each of,
are there more parameters in the TOGL layer or not?
Yeah, so there would be a bit more parameters in the TOGL layer indeed.
Okay. Yeah. But you're saying it's only.
Sorry?
Yeah, but you're saying it's only a little more.
Yes, I don't remember by heart, but it was not like massive difference. So it was really comparable. So then the first data set that we evaluate is basically like a synthetic data set where you have like two classes, first class on the left and the second class on the right, where you have like basically one would be like large cycles and the other one would be like a bunch of little and small cycles. So again, here you see that like just by the number of connected components should be like super easy, like for topologically aware architecture to distinguish between those two. And here we compare, so a GCN with a different number of layers. So here we have 0, 1, 2, 3. So basically that's the number of layers that you would have in your old GNN. And the blue one would then be like the same number of GCN layer, but with one which is swapped by with a toggle. And then we have like a WL, so classical like Weisfeiler WL test.
And for the WL node features, you use the node degree, right?
Yes.
Would this look different if we had like unique node features for every node?
Yes, so then you can do indeed like if you can do because then if you have like random node features, so in a certain number of so that's why the GCN is actually also like taking steam after like some layers, right? Because like if you do if you would give the GCN like only the nodes if you would only give the node degree, basically it would never be able to distinguish those ones, right? So the fact that it's actually able to distinguish those is because you have like randomness in the node features, which like after so many steps is going to be able to take this randomness and to figure out like if you are actually in a big cycle or in a small cycle.
Okay, what are your GCN node features?
So here, that's just random with the node degree. So in the GCN, we would add like the node degree and then like some random vector that you can just basically generate. If you just take the node degree, there is no way that actually the GCN is ever getting like 100% accuracy. So here, but like an easy way to distinguish between those two is basically if you just generate for each of those nodes a random vector, then after so many layers, which corresponds to like basically the length of your cycles, then the GCN is going to be able to compare intuitively, like if he has seen already like such such a node vector, and so basically trying to figure out if it's a cycle or not, or like what is the length of the cycle.
Yeah.
So, and that's exactly what this effect that you see here, because you need like 3 layers, so which corresponds like roughly to the length of like the cycles here, in order to figure out like what type of cycles this graph, so the GCN is operating on. In contrast, like when you have like the toggle layer, as we saw, like you directly have information about the topology of the graph, and so you can directly distinguish without even one GCN layer the nodes attribute, so being distinguished between those two graphs. So the second examples that we gave is like this one that we call the necklace data set, and here you can see like similar type of performance that like TOGL can basically like give you directly like graph level information that can be used like to distinguish between those two graphs, while GCN will need like multiple layers and iterations in order to distinguish between those two. Okay, so that was like for synthetic data sets.
So is my microphone good or is it a bit bad?
I'd say it's all right, yeah.
Okay. What did I want to ask? All right. In your previous experiment, so we have a bunch of GCN layers and then we have one toggle layer, or how does it work?
Yeah, exactly. So here I don't remember exactly where we would put it. So we would have so that would be, for instance, so here 2 would be like 2 GCN layers and 1 toggle layer. And I think if I remember correctly, we would do like k-1 GCN one toggle, and then one GCN.
Okay. Yeah.
So that would be the penultimate layer. Yeah.
It's, yeah, so highly. I think your microphone is having some.
Okay. So, if I'm not wrong, if you talk. Sorry, I was muted. Sorry, I wanted to ask.
Okay. Yeah, please just go on.
Okay. All right, so then we go to like the second experiment, where here we actually take like benchmark data sets, but in order to assess if like our layer is doing a good job in like extracting like topological information, we do a little tweak on those data sets. So it's very well known and like documented that a lot of graph neural network benchmark data sets already contains a lot of information only in the node features, right? For instance, in molecule proteins, like so I mean, like all many different type of graph neural networks, just encode like a lot of information just at this level. So without even using the topology of the graph. So in order to see if like our layer was like basically outperforming GCN in trying to find like in exploiting like topological features, we reused the same benchmark data sets, but we removed the information from the node features, from the node attributes. So basically, we would like do the same thing as I just explained earlier. So for each of those graphs, we would transform, we would replace basically the node features, the node attributes by random vectors of the same dimension. And that's what we call like structural data sets. And here we run our methods for like different backbones. So we use the backbone of a GCN, of a GIN, and of a graph attention layer. And again, here we chose like 4 GCN, and then we compare against like with 3 GCN and 1 toggle, and same for GIN and for GAP. And you see that like mostly on overall for all of this type of data sets, that our architecture is able like to better harness the topological informations in all those graphs. And do a better job both at graph classification and also at node classification. Quite overwhelmingly better. But then for sake of completeness, we will also like evaluate our methods with the full data set. So basically it's the same data set, but there we just keep like the initial node features attributes. And here you see that like the picture is a bit like more mixed, which actually like illustrates also that like when you have access to these node features, you can do you can improve the performance quite massively. And here we have like some wins. So we see that like basically TOGL is not always like much better. It is sometimes a bit better, but also like importantly, it's not like degrading performance very massively. So the only example, the only exceptions to this would be maybe like the enzymes data set, which is like also kind of a bit tricky to fit because like very small, so you overfit like very much very easily like this data set. But like overall for the other ones, so TOGL is either beneficial because like there is still some information left in the topology of the graphs that could be harnessed, or not detrimental, which is also what you want to do, because of course beforehand there is very it's not very easy to know if like the topology of your data of your graph is going to be important, or if it's going to be the node features of your graph that's going to be more important. And you see this also both for graph classification and node classification. All right, so time to wrap up. So what did we learn? And yes, please.
Oh no, I wanted to basically summarize, but I guess you're summarizing.
Yeah, yes, I guess. Hopefully. So so what we learned is that like, so when the topological structure is important, so basically in those synthetic data set that we created, where we enforce that it would be important, but also in the structural data sets, we see that the addition of a topology aware layer boosts the performance quite overwhelmingly, and it's quite clear that like it's very it gives a clear added value in terms of performance. So because we designed also this I mean our model to be basically a layer that we can stack at like any positions in the architecture, the position of where you're going to put this topological layer, and like also how many of them you want to put in the layer. So we only experimented by putting one of such layer in each architecture, is also an hyperparameter. That's funny. I see that's Prabhu's drawing on the slide. I didn't know you could do that. And so the position and the number of, or at least the position, because that's what we experimented with, it does impact the performance, but we don't have like a clear-cut answer to saying, okay, you should put it here or here. It's from our experiments, it seems to indicate that like it depends heavily on the type of data set that you're working on. Another question is that like here for computational reasons, we only included like a dimension 0, a dimension 1, Betty numbers, but could we also incorporate like higher order structures such as cliques? And so would it actually like improve the performance? Basically here so I think there is still a lot of questions about like what, and I think that's also sparked maybe a discussion that we can have like in a general group together, is that like how can we basically learn important topological features, and which relates to like how do you learn a good filtration function? So it's still a bit unclear about like, okay, so how this learning this filtration actually is going to do like a much better job than basically like having a random filtration and a bank of random filtrations that will basically pick up some signal, because for instance for the Betty numbers, you will still see, for instance, like very, let's say, basic features. You're still going to see them with a random filtration. There is still like, I guess, where can experiments to be done is that like, how do we learn a good filtrations, and how much do we gain? How much do we gain for this? So that's it for us. So thank you very much. Just still a little catwalk of all the beautiful people that actually collaborated on this project. So please don't hesitate to check out our paper. The archive is here. It's also on open review. And yeah, and if you have any questions, like please don't hesitate to reach out, and we'd be pleased to answer all questions.
Perfect. Nice. Thank you for the overview of your paper. And yeah, I just really like the paper because it's a nice idea. You test it with the appropriate stuff, and we see all of the results. And I think you're very honest in your paper about what makes sense, what works. Yeah, and yeah, so thanks for the presentation. And like, do you ever use multiple toggle layers, and does that ever help for a task compared to one?
Yeah, so indeed we never really use like multiple ones, but that's probably definitely like an experiment that we could also check. So here we were really interested in like from a purely scientific perspective and just assessing, does it help, yes or no, and just like with having one or not. But that's definitely something that we could also try, just checking if having multiple of those could also help. Also something maybe that I forgot to mention is that like, so this filtration function, just also maybe just to help people build intuition about what this whole architecture is doing and what this whole layer is doing. So we define like this filtration function that applies on each node of the graph. But this filtration function, you could see this as basically all of the previous layers before the toggle layer. Right? Because like, of course, you start with a graph that you input to your graph neural network architecture. And this graph, so all of like the GCN layers or like whatever GNN layers that you use are going to update the node features of each of the nodes, such that even if you then apply at layer 3, like a small MLP function that goes from RD to R, at the end of the day, this will build up, it will build upon the previous node features transformations that have been learned in the first layers of your architecture. So somehow the filtrations that you're learning is learned by the whole all the layers which are below your topological layer. And I think that's important to note.
Okay. And would you agree with my, or where don't you agree with my conclusion that you basically, in your experiments, you show that TOGL can capture, or that TOGL is able to, can capture topological information of the graph and can use it to make its classifications, and then you go ahead and show that TOGL doesn't really give us a benefit on the real world data sets. And our conclusion can be, for the real world data sets, the topological information isn't really that important.
Yeah, so that's a little bit the conjecture, right? So I guess it's not that like the topological feature is not important. I would say maybe there is less to, on some of those data sets, there is less to win from a global view of the graph. That's what I would say. Because of course that two nodes maybe are connected to each other, like might be very important. So here you see that we use like still 4 layers of GCN, right? So it means that like you can still have like a 4-step distance in between each one. So probably like, so the local topology of the graph is encoded, of course, in those architectures. So what I would rather say is that like the overall, so the global topology of the graph might be less relevant, though it seems that like in some, especially here, for instance, like in IMDb, it seems that like higher, like more global topological information might be useful.
Yeah.
So I wouldn't go as far as saying that like this is a good test to know if like topology of the graph is important or not. But I guess it gives it like some hints, and I guess that's also like one of our conjectures, that it's also working a bit not as good because the overall topology here is less important, or at least is taken over. You have as much signal by just using the node attributes.
Okay, so then can we say that maybe topological features like triangles, or like triangles are pretty important most of the time, but if we have our node features, which are most of the time different, and we have a GCN with enough layers, then we can capture that information anyway, and something like TOGL is not needed.
Yeah, but I think, I mean, one of the power of this is, for instance, you could check very easily like how far are like different substructures of the graph, for instance, because you could like the GCN might, for instance, build like some representation that like you have like a let's say you have a graph which consists of like 3 substructures, and then you're gonna be able, for instance, to like encode like the fact that like, okay, this is a substructure, I have like a GCN that works on the substructure. And then like with your filtration function, maybe you're gonna actually assign a different values on specific nodes of those substructures, such that you're gonna detect maybe a cycle in between those node structures in a much more prominent way that you would do with a GCN. So because you wouldn't be able to have like this global vision.
But your TOGL can do that, right? Because we have the filtration in there. We see that some node over there, or in some substructure over there, we have a cycle.
Yes.
And that's what you're calling global topological information, like that my node in my left substructure can know about the cycles in the right substructure.
Exactly.
But you're saying that this global topology maybe isn't the most important.
Yeah, so that's the big question, I would say. So is it or is it not? So I guess it depends on the data sets and like what type of information is encoded there. So I mean, personally, I would think that there must exist somewhere where there is, and that's what we also see, for instance, so it is IMDb, in DD as well. It was very prominent that like signal was quite strong, that you could.
What is DD?
The DD is also a protein, so bioinformatics type of graphs.
So is it a protein-protein interaction graph or something like that?
Yeah. something in that line. I don't remember exactly the details of this data set, but it's yeah. Which is funny, right? Because then like if we just like kind of blindly apply to all those data sets without like having the expert knowledge, so we just then infer a posteriori that like, okay, probably here the topological information is important or not. So I guess like a very fine grained like analysis of those graphs would also require maybe some expert knowledge in figuring out if that makes sense, that like the larger topology of the like the global topology of this graph was indeed important in that area or not.
And do you Hussein, you go ahead.
Sorry, I have a bunch of questions. Just wandering around from the beginning. For example, so when I haven't read the paper, by the way, so thanks for the presentation. So when you introduced this Betty number, basically, so Betty number is a topological invariant of basically of manifolds, complexes, whatever you define as your basically the representation of your space. So I was wondering, like, how should I ask this question? So how do you think that the Betty number is an ample enough topological invariant to define or to express a certain graph, since we have like also like different types of topological invariants that at least for manifolds, smooth manifolds in differential geometry, you can define different topological invariants, and they might be related in some cases, they might not be related in different cases. So how do you, in general, say that having persistence, computing the k-Betty number for a certain graph, like constituents of a graph, is enough to express the topological, quote-unquote, properties of that graph?
I don't think that's a fair statement, right? That it's never said that the Betty, or like having the first two Betty numbers completely captures the topology of a graph.
No, I'm not saying that this is being basically said in the paper. I'm just asking, like, from the research point of view, for the like future works, like how do you like, looking at the data set, looking at the graphs that can be created from the data set, like, how do you say that the certain Betty numbers or basically a certain topological invariance? For example, you can also take a look at the volumes that these you can create from the simplexes that this graph creates. So how do you compare the results from looking at the Betty numbers, Betty numbers, and for example the volume of one simplex or two simplex of the graph?
And maybe to add on to that question, like, are there any other topological features that you would see as especially promising and would like to find a way to encode as well?
Yeah, so thank you for this question. I think indeed, like as Hannes pointed out, we don't claim that like it's enough. And of course, I think it would be really interesting is like figuring out like what other type of topological features might be interesting to capture and to compute also in this approach. So like the most obvious one, for instance, would be like to take like Betty number. So something also I wanted to add with respect to your question is that like also so of course it's only the Betty number, but like we just check the persistence of it, right? Which is like gives you more information because than just like having just a snapshot at the graph at a single time step. So the fact that we actually have this filtration and we check the persistence of the Betti number, it gives you much more information than just checking the Betti number of the graph G, right? And so that's gives you also how prominent this feature is. So I think that's the first important point to clarify. Then the second one is that, like, okay, so one obvious one would be indeed like to check like K2, so like the number of clicks. Why we didn't do this is that, like, because like K0 and K1 is like the easiest to compute, and also from a computational perspective, like the less expensive. So there are other graphs, other works that actually try to capture like more complex topological features, such as number of clicks. But because of this computational overhead, they would have to compute that like offline beforehand. So not with a learned filtration function, but they would just actually like learn those persistence diagrams on the row graphs, store this, and then use this information then to feed to the network, which is actually like kind of like a very interesting and also a valid way to approach this. But that also let's say illustrates why also like different type of topological invariants might be like much more expensive to compute.
And so what is the what is the complexity of computing higher Betti numbers?
So basically for instance in K2 you would have like to check like the number of clicks. So you have to check if you have a click in the graph. So it would grow exponentially with the number of nodes, I guess, here.
I see. Okay. So
it quickly becomes because K0, the number of connected components, is very easy to compute, of course. And then the number of cycles, you can also like manage that. Then like, yeah, number of clicks would be a bit more complicated.
Okay, so by this number of cycles, you mean like 1 cycles, right? Not 2 cycles, or
yeah.
or what you call clicks, right?
No.
Yes. Yeah, so
cycles, right?
That would be, yeah, like a cycle in a graph. So basically, where you can, it's not an acyclic graph anymore. So here you would have 1 cycle.
I see. Because I asked this question because there was this also paper like from, I don't know, 3 years ago that people tried to compute the volume of simplexes as a topological property of certain graphs. That I don't know, the name of the paper was like logic and transformer of 2-cycle transformers, some two simplex transformers, something like that. And this was I can find out the exact name of the paper. So in that, people were trying to again for graphs, they were trying to find out the volume of tetrahedron that is being embedded into an Euclidean manifold, and the volume of volume is definitely is a topological invariant. Basically that's they went to from like 0 simplex to 1 simplex and to 2 simplex as well, or I think 1 simplex at most. So it means that the volume of the tetrahedron. So that approach is different from yours, which is computing the persistent Betti number. But as I said, I haven't read your paper. If there is a comparison between your work and their work, like how strong you guys, either of you, capture any topological information. So that's why I asked this question. That what is the threshold to understand like which topological invariants or how many topological invariants to consider is important in the end to capture like the most topological and global information of a graph. And for sure, there is also always this computational complexity on the way of computing higher order interactions between the nodes in the end. Yeah. I can find the exact name of the paper and just put it on the comments.
All right, that would be nice.
Yeah, sure. Yeah, thank you.
Know what the volume of a simplex is?
Basically, you're asking me or
asking Edward, but yeah.
Okay.
I mean, yeah, let's go with Edward.
No, so I don't know. So it would be I don't know this paper, and also it's I don't know, like from just like this, it sounds weird to me that like the volume would be like topological invariant, because of course like if you would just like put them like further away, like the volume would change. So intuitively it doesn't sound really topologically invariant to me, but I would have to read that paper as well.
Yeah, but a volume probably means something different. Like we also have the volume, right, where we the volume of a node being the degree sometimes. Bastian, do you know what the volume of a simplex is?
There's multiple definitions, which is why it's a little bit hard to say what the authors mean. So in the easiest case, if you're actually looking at simplices as convex subsets of a space, then it's some weird determinant expression. I'm saying weird because I never recall the order of the terms, but essentially it involves solving a determinant, and then you scale it by 1 divided by n factorial, where n is the number of vertices in the simplex, or rather, no, it should be n is the number of vertices plus 1 or something. Yes.
Yeah.
Okay.
Yeah. So that's a geometrical definition. So maybe to reduce some confusion, not diffusion, maybe to reduce some confusion in the terminology, we are looking at this purely from a topological point of view. So we don't necessarily incorporate distances or metric information into the graph, other than what is already being encoded, of course, with respect to the node attributes, or with respect to other attributes that we can leverage. But we don't have a notion of distance in there. Whereas if you want to build simplices based on geometrical realizations of data, that also works, and then you can use these kind of volumetric formulas, for instance. So it's a little bit of a different viewpoint.
Am I getting it right that a volume is not a topological feature? Like it depends on the geometry.
I think, yeah, I think I would definitely say, and now, well, I mean, this is now being recorded, so everyone can then laugh at me afterwards, but I would say that it's not necessarily an invariant, because as Edward pointed out, you can of course change the coordinates of that simplex, and that will change the volume. Whereas we are looking at things that remain invariant with respect to certain transformations of the graph. So for instance, if you would give our graph some kind of coordinate system, this wouldn't really change the number of cycles or the number of coordinates. This would only change their size, as it were, or their distance, right?
Yeah, okay. I think that's enough volume sidetrack, but thanks for the quick overview. Let's maybe get to Johannes's and John's points. Johannes, or maybe John, go first.
Yeah, sure. Yeah, this is sort of a follow-up to the previous question. And I haven't read this paper on graph filtration learning, so maybe I need to read that first. But I was curious, when you talk about topological invariance, I mean, on a discrete structure like a graph, topology isn't at all defined, at least in the context of, what we understand from a continuous space, right? So I was wondering, when you say topological invariant, how well defined is that in the context of, what we understand topological invariance from a continuous, continuous space? I know that you have this notion of this persistence, so I guess the filtrations are sort of like, would be like analogous to some sort of diffeomorphism or something, some sort of transformation on the graph. And then you have persistence of those features, which are kind of like what you're calling topological invariance. But I was wondering how well formalized this theory is to these discrete structures.
So I would say quite well, because actually, like, so the graph itself, like, imposes like a connectivity, and so basically a neighborhood on each of the nodes, right? So basically you can definitely apply all of like the computational topology tools there, because like your neighborhood is defined by like what are the different edges that connect your node to all of the other ones. So I don't know if that.
Yeah, but we don't have any
question.
notion of you know, differentiability, and we don't have anything like a metric tensor. There's no way to define a manifold. You know, a graph isn't a manifold at all, and there's no notion of a metric tensor, anything that you would need to define or any sort of geometric information. You can by hand, you can impose features on the graph and call them sort of geometric or topological features, but the question is like whether they, you know, you'd have to show in the continuum limit that they'd actually reproduce what you would get on a continuous manifold, I think, in order for them to be.
Am I getting something wrong here, or aren't like geometric and topological features two separate things, like two very different things? And
yeah, they are different, yeah. But even defining like a topology on it, I mean, if you want to define a topology, I'm talking about the formal definition of a topology. I guess what I'm asking is, are these what you're calling topological features? Are they actual, you know, how well defined is this notion of doing topology on a discrete?
So is it like, yeah, how much does the word topology that we use for graphs, how much does that actually capture, or how does that relate to a formal topology in mathematics?
Yes,
like
exactly. Exactly.
Sets, and then we can define a topology on the set.
Exactly. Because I see like the motivations are very similar. I mean, you know, you have these what you're calling these persistent features, you know, through the filtration, which are what I think are kind of what you're calling these invariants, topological invariants, which makes sense. But I was just wondering, yeah, kind of how well formalized the theory is.
Well, my guess would have been that there's like no relation really, and it's just the same word that we use for topology and graphs and topology, like a real topology defined on a set. But yeah, let's see what the experts say.
So I don't consider myself an expert on the topic, but I would say, and also like, you know, I think I would have to look up like how people actually like really like rigorously like define this link. But it seems to me that it is still like very much supported in a sense that like a topological space, and it's basically kind of a set, and then like the notion of like open sets also on this initial set, right? So here you could have like the set of nodes, and then your open sets would be defined basically by your connectivity of the graph, right? That like you would have like open sets would be basically your neighborhoods, and then as soon as you have that, then basically like you have a topological space, and hence like an induced topology on your space of vertices.
Yeah, that's nice.
Precisely, yeah. To maybe add to this, I think what we're seeing here is kind of the disconnect between algebraic and differential topology, which are a little bit of different branches, and they look at the same things but with different lenses, so to say. But the study of graphs as topological objects or topological spaces per se, this is something that has been going on for decades now. And you can assign, I mean, a topology in the sense of a topology is just an assignment where you say, okay, this set is open and this set is closed, basically, with some constraints, of course. I mean, you have to follow some rules, some axioms here, but you can always define this. Now, what this persistent homology stuff does, it arises from algebraic topology, where people came up and said, well, we have these complex continuous objects like a manifold, like a sphere, like a torus, whatever, but we actually want to do some algebra with them. So we want to do some calculations with them. And we are sufficiently, well, we are okay with reducing them to a simplified form, while still capturing some kind of characteristic features. And this is where you get some kind of some things like a triangulation or a simplicial complex and these sort of things, which are all kind of discrete ways of describing continuous objects, but always with the added thing that, formally speaking, a triangulation, for instance, is always imbued or endowed with an additional homeomorphism to your nice object, to your natural object in some sense. And so yeah, I think that what persistence does, or what persistent homology does, it tries to bridge these two worlds. But I of course understand that it's different from differential topology or Riemannian geometry, or where you would say, this is my manifold, this is my metric tensor, and now we can calculate something. So I think this contrast is particularly apparent in these recent ideas of curvature calculations, where you have a well-defined notion of curvature on a Riemannian manifold based on the tensors, based on its tensors. Sorry about that. But as soon as you go into the discrete space, then there's the question like, okay, what does it mean for a graph to be hyperbolic, or what does it mean for a graph to be flat? And then you end up with these appeals to metaphors, or with these appeals to analogies, like form and Ricci curvature and stuff like this. So basically the stuff that Michael Bronstein and his research group, for instance, I think Francesco Di Giovanni is interested in. So maybe that helps a little bit. This was a little bit more of an info dump, but I'm happy to expand on certain things, of course.
Yeah, thanks. But so first of all, I was completely wrong, obviously. But also, Edward, can you repeat our set, are the nodes, and what are now our open sets?
That would be the neighborhoods.
Okay, but of arbitrary sizes, right? Neighborhoods of sizes.
Yes, I think.
Yeah,
because they would define like how they are connected.
Okay, good. Then Johannes.
Hey, thanks for your talk. I was wondering, since your filtration function takes as input the hidden states of nodes at the kth layer of your GNN, I guess if you place your toggle layer early on in the architecture, then the input of your filtration function is based on a local view of the graph. And if you place your toggle layer in a later layer of the GNN architecture, the input to your filtration function becomes more global.
Indeed.
And so I was wondering, did you experiment around with where you want to place your toggle layer? I mean, since you produce a global view in the toggle layer anyways, does the placement of it matter at all?
Yes, so indeed, that's a very good point. And so we actually experimented a lot in the position of the layer, but we couldn't see like a clear trend or like a general trend. But we can see that there is a difference of performance on a dataset to dataset basis. So some datasets seems to actually support like having like a toggle position higher up in the architecture. Other ones like a bit like bottom down. But you're right that like indeed, depending on the position, it will like the filtration will have like more local or global information. But so yeah, the answer is there is an effect. We haven't figured out like how this plays out at the general level, but we can see that like it's an hyperparameter, and then like for different data sets, you should experiment with different positions.
I mean, it might be overkill, but one thing which could be interesting to try would be to have a TOGL, the diffusion improves graph learning layer, which creates hidden states which have a global view of the graph already, and then put a toggle layer on top, because then the input to your filtration function is global in itself, and you produce an additional global view of the graph. This would be, in some sense, an experiment where maybe you have the most global view possible. But did you think about that? Or?
So like
no, not really. So, yeah.
You mean we have TOGL, toggle, then the rest of the GNN?
Yeah, exactly.
Okay.
Yeah, I mean, I think there is kind of I mean, there is some, I mean, like kind of like different intuitions also colliding here, because like the filter, so it's like the toggle layer is supposed actually to provide like global information, but not exactly the filtration function. So of course, like one can, if you already can provide like with some like global level, probably like it does a better job. But I guess if you just like have something which already contains all the global information, probably like a topological layer is not even useful anymore, because like you already have, already all your graph. Or I mean, that would have been to see, but like that's basically also the goal of our layer, is also to provide global information.
Wait, but we have global with TOGL or TOGL. We have, right? We don't have the global topological information.
No. So, but I meant that like, so if we want to put like all already like, so like one of the motivation of our work is like, of course, like encoding like topological information, but also by doing this is also like having a kind of a global view of the graph, right? It's like be able like to have a kind of bird's eye view on the graph rather than just staying local, and that's what also experiments suggest. So then let's say it's not like competing methods, but just like putting all of like this global view already in the filtration function might be super interesting. But of course, it's kind of like a different type of experiments is what we were trying to do, right? I don't know if you see what I mean, but like our initial motivation was the topological features and providing global information. But I agree that it would be an interesting experiment.
Yeah, if I understand correctly, you're saying the question is how large would be the overlap of the global information produced by a TOGL layer and the global information produced by a TOGL layer?
Yes.
And I guess I don't know, because they're based on different concepts, right? In one, you have a diffusion over the entire graph, and in your case, you collect topological information. I don't really know. But thanks
no,
again.
I think those are really good. Yeah. That's a very good point. I think it's worth trying out. Thank you.
Yes, very, very nice point. Just, yeah, and then any other points like that? Or otherwise, I'll say thanks to Johannes, thanks to Hussein, John, and whoever else I forgot for asking the nice questions and spurring some more discussion.
Yeah, thank you.
And then lastly, also thank you for answering all of our questions. And yeah,
It's always nice to have a great discussion with great people. So thank you for the invitation. I think it was we were very well welcomed. So that's great. And yeah, so please reach out to us if you have like any further inquiry or any ideas and things like that. We'll be really happy to answer them.
Perfect. All right, then let's call the day for today and see you all next week, I hope, for our next paper.
Thank you. Bye-bye.